Hi everybody, hope your day is going well. We're continuing to work on the same standard that we worked on previously, finding critical points, finding and justifying increasing, decreasing, and constant behavior, and then finding and justifying extrema, giving a local argument or a global argument as appropriate. So over here we have a couple examples. Again, the graph of f of x is shown, and they want us to sketch a graph of f prime of x, the derivative. And if I look at this particular graph of f of x, the slope over here is always going to be 0. We have a horizontal line, and that has 0 slope. And so my derivative over here is going to be this horizontal line at x equals 0. The next one over here is I have this graph f of x. Over here, my slope is going to be negative for all values. It is going to be a constant negative value. And so you're going to end up with something that looks like this. You're going to get a horizontal line. I don't know exactly what negative value is going to be. It could be -2, it could be -10, it could be -100. It depends on what's going on with the y and the x scales, which definitely aren't marked. The next one over here, again, we have a derivative. The derivative is going to be negative in all of these regions. But over here, close to this edge, it's going to be close to 0. And over here, it's going to be also close to 0. When you get over here into this region, it's going to be a very large magnitude negative number. We don't really know 100% for sure with this graph whether we have a vertical tangent or if we have a point where the derivative gets to a very large magnitude negative number, like -1,000 or something. There's basically two options for that. But either way, all my derivatives are negative, and so I'm going to be below the x-axis. They're going to be close to 0 on that side. They're going to be close to 0 on that side. In the middle over here, we have a couple of different options. One option is we have that vertical tangent over there, where the negative values for the derivative become unbounded. They're going to go to that negative infinity. In that particular case, our graph of our derivative is going to look something like this. And that is a legitimate possibility. It's probably the way I wanted to draw this graph when I did this many years ago. And we get a graph of the derivative like that. The other option is it's a very large negative number. If that happened, we would get a graph that does something like this. We don't have the vertical asymptote. It's going to go down to this very large negative number over there, and then it's going to basically come back up. But either way, as far as AP Calc goes, as long as you can identify when the derivative is negative, when the derivative is positive, and just relative magnitudes of those derivatives, you will do super awesome as far as any test questions that are given. You guys try our last one. Welcome back. If we go through and try to sketch derivatives, the slopes over there are going to do something like this. We're going to have positive slopes, but then we're going to have 0, and then we're going to have negative. And so somewhere right over here, we're going to have a value of 0 for the derivative. When we're to the left of that number, we're going to have positive values. And when to the right of that number, we're going to have negative values. As we go further to the left, the values become bigger positive numbers. And as we go further to the right, they become larger magnitude negative numbers. If this happened to be an x squared graph, you would get a line. It may not be an x squared graph. It may look something different, but it looks pretty close to an x squared graph, so I drew it as a line. This question comes from 2015 test. It was question number 5. It was part A. It is a no calculator question. It is a very common question. If I had to bet money, I would bet a large amount of money that you would get a graph of a derivative on your free response exam. It seems like these graphs of derivatives show up basically every single year. It is a significant portion of your exam. They want you to be able to analyze functions. When they don't give you the graph of the function, they give you this other information, which is this graph of the derivative. The figure to the right shows the graph of f prime, the derivative of a twice differentiable function f on the interval between -3 and 4. The graph of f prime has horizontal tangents at -1. So -1, we have a horizontal tangent. At x equals 1, we have a horizontal tangent, and at x equals 3, we have a horizontal tangent. The areas of the regions bounded by the x-axis in the graph of f prime at the intervals between -2 and 1, 1 through 4, are 9 and 12, respectively. And so we didn't get to this yet. We're not going to get this till chapter 4. But those areas over there are going to be 9 and 12. It's not really applicable for this particular problem, but they gave us that information. Part A, they want us to find the x-coordinate at which f, graph not shown, has a relative maximum value, and then they want us to give a reason for your answer. If you truly learn how to find maximum values, you'll say, hey, I got to go find where the derivative of this function changes from positive to negative. These questions are super easy. Hey, look at this. I got a graph of the derivative. If only I could identify where the function f prime changes from positive values to negative values, it would be super easy. Hey, look at that. Right over there at -2, f prime is changing from positive to negative. That over there is going to be my relative maximum. They're asking for just the x-coordinates. That x-coordinate is going to be x is equal to -2. They want us to give a reason for our answer. And I didn't do the best job of this in the previous one. But again, we really want to try to make sure that the grader is aware that we fully understand this question. And so it would be good to say something like this. This is the only point. And the reason why I'm doing that, this is the only point, I want to try to indicate to the grader that I looked everywhere. I did truly analyze the entire graph. I just didn't stop and give up after I found one value. But this is the only point where f prime changes from positive to negative. The other way you could do this is you could say something like f prime changes from positive to negative at x equals -2. Okay. Next question. This comes from 2013. Is question number 4. It is parts A and D. It says the figure above shows the graph of f prime, the derivative of a twice differentiable function f, on the closed interval between 0 and 8. The graph of f prime has horizontal tangents at 1. And so we have a horizontal tangent here at 1. At x equals 3, we have a horizontal tangent. And at x equals 5, we have a horizontal tangent. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. The function f is defined for all real numbers, and it satisfies that f of 8 is equal to 4. And a lot of that information we don't need yet. We'll talk about that when we get to chapter 4, but we're not there yet. Your turn. Find all the values of x on the open interval between 0 and 8 for which the function f has a local minimum. Justify your answer. So give it a shot. Welcome back. This point over here is the point where f prime, the derivative of the function of interest, changes from negative to positive. We're trying to find where f has a local minimum, which means we're trying to find where f prime changes from negative to positive. And that's going to happen at x is equal to 6. That is the only value where that happens. This is the only point where f prime changes from negative to positive. Part D, the function g is defined by g of x equals f of x cubed. If f of 3 is -5/2, find the slope of the line tangent to the graph of g at x equals 3. Pause if you need to quick do this. Okay. And so we want to find the slope of the line tangent at g, which means we need to find the derivative. G prime of x is going to be 3 times f of x squared. Take the exponent down in front, decrease it by 1, multiplied by the derivative of what's inside, and we get f prime of x. We want to find this particular value at x is equal to 3, and we get g prime of 3. That's going to equal 3 times f of 3 squared times f prime of 3. And if we go over here and look at that, that's going to be 3. They told us that f of 3 is negative 5/2. That was super convenient. This is going to be this negative 5 over 2, and we're going to square it. And then we got to find f prime of 3. How am I going to find f prime of 3? Well, I got to go over here to my graph. This is a graph of f prime. And they just told me when x is equal to 3, this again is f prime over here. The y values are f prime values. F prime is going to be this 4 value. This is a graph of the derivative. The x coordinates, or the points on this graph, tell me what is the derivative, f prime, at every single x value. And so that derivative over there is going to be 4. We can go and fill this out. Negative 5 over 2 times negative 5 over 2 is 25 over 4. Times the 4 is just going to be 25, and then times the 3 is going to be 75. Our last problem, try that one out. They're asking us which graphs, f, g, or h, have a relative maximum on the open interval between a and b, and they're giving us derivatives. In order to have a relative maximum, the derivative f prime has to change from positive to negative. Do these derivatives ever change from positive to negative? And the answer is right over there. F prime changed from positive to negative. The next two graphs, that never happened. It changes over here from negative to positive, but that's not what we're looking for. We're looking for a maximum. And then the other one over here, the derivative is always positive over there. We don't have any changes. And so we're going to get F only. Hope our lesson made sense, and I will see you guys next class period.